Okay, morning everybody. Last time we were talking about the corrosion cell and how corrosion obeys Faraday's law of electrolysis. So Q equals ZFM, the charge, which is IT, equals the number of electrons involved in the reaction multiplied by the Faraday's constant multiplied by the mass, the molar mass of material in the reaction. So we can get a kinetic handle how fast the corrosion is occurring by looking at the current flow through the system. And all corrosion processes obey Faraday's law. So it doesn't matter whether it's general corrosion or localized corrosion, stress corrosion, cracking, corrosion fatigue, etc. The only exception is hydrogen embrittlement. And that's what we're going to talk about next, to just give you the basics of hydrogen embrittlement. You did a while back get this handout which has the three localized applied stress mechanisms on it, and then this on the other side, and I've got some spare copies if anybody wants another one if they haven't got one. Everybody got one? Great. Okay. So hydrogen embrittlement is not a corrosion process in the same way. Yes, you get cracks in the material. Yes, they will cause failure of the component, but they're not controlled by the current flow in the process. So all these corrosion processes that we're thinking about are all anodic processes. So the structure is at a corrosion potential, some anodic potential. Whereas in the case of hydrogen embrittlement, quite often the structure is at a cathodic potential, and therefore it cannot be corroding. On your handout you've got this image which illustrates the difference quite clearly. What we've got is a stress corrosion crack on the left hand side growing at right angles to the applied load, and we're getting dissolution of metal at the anode tip of the crack. And if we do a plot of current for the material, we're dealing with anodic currents. We're getting metal being oxidized and giving up electrons. In the stress corrosion crack version, things are a little bit different. What we are doing operating in the cathodic current region. So we haven't got any oxidation going on, and the mechanism is one of hydrogen being absorbed into the matrix of the metal or alloy. and quite often there's a reduction process going on. Hydrogen in the solution plus electrons are generating hydrogen atoms that can be adsorbed into the material. So it's a cathodic process, entirely separate. There are situations where you get changes in polarization, so that you might go from one anodic situation to a cathodic situation over a period of time, but the two mechanisms themselves are very much separate. Yes, absolutely.
Regarding this embrittlement and this one, corrosion rate, so do they have some difference in, like, maybe color? No? Can we identify?
Oh, can you identify it? Well, I'm going to tell you about the hydrogen embrittlement in a minute. Yes, quite often there are a number of features that make it different. One is that you're likely to get corrosion products, so you've got oxides and magnetite perhaps, or a passive film. The other thing is, as in the drawing, the cracks are just that little bit wider. These tend to be sharper and narrower. What you actually find, we're sort of jumping ahead, but the growth rate of these cracks is limited by the current flow. These go much faster, considerably faster. There's definitely a different mechanism. Okay. So yeah, in a lot of situations, you're going to be able to identify that these are stress corrosion cracks. The reason why I was hesitating is I realised I've got my sequence of slides slightly out of order. So apologies for this, but I'm going to give you these two slides at any rate. So we've jumped slightly. This was something I mentioned last week, but I just wanted to remind people and make sure they got it clear in their minds. So this is about the anodic corrosion. This is the stress corrosion cracking, general corrosion, pitting and so on, before we get onto hydrogen. So this was just to say that we were interested in loss of through-section thickness. That commercially, that's looked at in millimetres per year, or in the United States in milli-inches per year, and that sometimes causes confusion. So you've got to remember that there's a conversion factor here. And looking at through section thickness loss is fine for general corrosion situations, and that's indeed what's done for insurance purposes. The trouble is, once you start getting localized corrosion, you might have a structure that looks pretty good, but in fact has got a hairline crack in it, or a big pit in it somewhere. All this measure of current in the corrosion cell is about the kinetics, how fast the reactions are occurring. So previously, when we were talking about potentials, we were interested in the thermodynamics of the reaction. It's the current that tells us something about the kinetics. Okay. So we want to measure the current flow, and that is limited, fortunately, by aspects of ion migration and diffusion through the electrolyte. And we're not just talking about the migration of ions to the anode, or diffusion of gases through to the anode. We're also talking about the cathode process, because one can limit the other. So if there's a slow cathode process, the anode process has to go on equally and opposite, and so there'll be a slow anode process as a result. Okay. Right, so that was that's connected with corrosion and currents. I'm sorry we got the order wrong there. Hydrogen is a cathodic process which doesn't obey the same criteria. So let's go back to hydrogen embrittlement. It sometimes gets given different names. You get hydrogen-assisted cracking, you get hydrogen-induced cracking, or hydrogen embrittlement. You can take your choice. And hydrogen is quite a tricky sort of material to deal with. It's colourless, it's odourless, it moves fast through materials, so it quite often gets used as an explanation for odd failures. Clearly, if you've got loads of corrosion product around, then you're at an anodic potential, and so it's not hydrogen embrittlement. But your first question really is, where do you get the hydrogen from? If you've got excessive cathodic protection, you effectively electrolyse the electrolysis occurs of the water. So you break the water down into hydrogen ions and hydroxide ions, and those hydrogen ions can discharge and be adsorbed into the cathode. Another possibility is damp welding conditions, and that happens quite often in the real situation. If you're out in the field welding pipes together, damp welding consumables is another possibility of introducing hydrogen into the welding area. When you electroplate components, you cathodically polarise them, and if you get the polarisation slightly wrong, then you can start getting hydrogen absorption. So things like chrome-plated hydraulic pistons and that sort of thing can get be a source of hydrogen induction into the material. So you first got to decide where the hydrogen's coming from. The failures themselves are quite often intergranular, sometimes transgranular, and the cracks tend to be fairly clean and sharp. And because it's not dissolution controlled, the cracks move pretty fast, orders of magnitude faster than stress corrosion cracks. Okay, so they move through the material quite quickly. And so you get some quite disastrous failures, quite rapid failures of components. Okay. Where's that? So, what do we know about hydrogen embrittlement? We know it's affected by temperature. I've said the cracks are very fast. We know that the crack growth rates are high. And we also know that the presence of some species in the environment actually enhance the absorption of hydrogen and so make the materials more susceptible to cracking. And we are dealing with adsorption here. In spectroscopy you get absorption with a B, but here it is the adsorption of the hydrogen into the material. And that process, as I say, can be assisted by the presence of some elements. It can also be slowed down in some situations. So there are protective oxide layers that can form that actually make it more difficult for the hydrogen to get into the metal. Okay, so sometimes if you've had a little bit of general corrosion first of all, and you've built up an oxide layer, then the hydrogen won't go into the material. So there's definitely a surface condition effect on the adsorption. And we are talking about absorption of hydrogen as hydrogen atoms. So we're not talking about H+, which is actually a proton and doesn't exist, but you might then decide that it's H3O plus a hydronium ion. We're not talking about that. Inside the metal, we're talking about hydrogen atoms migrating. We're not talking about hydrogen molecules. Okay, they're bigger and slower. We're talking about hydrogen atoms and not charged species only. Okay. The mechanisms that have been put forward are varied depending on the type of alloy and situation you're in, and I've put them down there in order of preference. So the first mechanism relates to the stresses in the alloy or metal, if you like, almost stretching the lattice a little bit and making it easier for hydrogen to go into the lattice in the stress region, and embrittling the material so it's then more likely to crack. And that is a mechanism that can be applied to steels and other alloys. Hydride formation is a bit more special. It does definitely occur, but it only occurs in things like zirconium alloys, palladium alloys, and hafnium alloys, those sort of things. So hydride formation doesn't happen in steels. It only happens in particular elements like zirconium, Zr, and it'll produce ZrH4, so you remember. And so you can think of this just like the formation of an oxide. Okay, in this case it's just produced a hydride, and it does the same things that an oxide does. Do you remember the volume of the corrosion product is greater than the volume of the parent metal? The volume of the hydride is greater than the volume of the parent metal, so the whole thing expands. And we did some experiments some time ago, and we were using palladium cubes. Okay, cube of material, and if you cathodically charge a cube, you end up with a sphere. So it swells and forms a football. Yeah? And that's purely because of hydride formation in the material. So it definitely happens in some materials, and of course a load of cracks. But it doesn't happen in steel. So as this one's less interesting for you, but definitely occurs. And I'll show you an image if it'll behave itself. Yeah, not too bad. So this image here is of a, it is actually a zirconium sample. And these little black features here are small intergranular cracks associated with hydride formation. And I don't know whether you can see really at the top here, but the specimen seems to be bowed. It's sort of swelled up, particularly in this region here. And that's because you've got more and more hydride there. The point of entry for the hydride was here. It's actually was a spot weld on the material, and that was a good place for the hydrogen to get in and start to attack it. So there's definitely a mechanism for hydride in some metals, but not steels. The mechanism that I think you guys get told about elsewhere is this one, where they say, oh, the hydrogen goes in, it goes into voids, and then it pressurizes the voids, and that makes them open up. And certainly there is some evidence of gases causing delamination of coatings and so on. It depends how you like these things. My trouble with that mechanism is atoms and indeed molecules have a tendency to migrate down concentration gradients. So if you've got a partial pressure of hydrogen, hydrogen atoms on the surface of your electrode, and you've got a void somewhere inside the electrode, why would the partial pressure of hydrogen inside the void be greater than the partial pressure of the hydrogen outside? The answer is it wouldn't be. They should be the same. The thing gets slightly tricky if you then say, oh, but this hydrogen now converts. So 2H dot goes to hydrogen molecule. Then you might say, yeah, okay, there's a possibility that this partial pressure is not identical to that partial pressure. But it won't be hugely different, because this, like all reactions, is some sort of equilibrium. And so there's some equilibrium of migration, diffusion through here. Remember, the hydrogen moves very fast through the material. So, although this theory has been put forward, and there probably are some interesting bits of evidence, what I'm struggling with is the equilibrium between the partial pressure outside and the partial pressure inside. I'm also struggling a little bit with why there are a load of voids being formed. If you've actually got to the point where the stress is high enough to cause voidage, it's probably high enough to cause mechanical cracking, and then you don't need any hydrogen. So it becomes almost like a fracture toughness problem. So I've put all the mechanisms there. People are still working on it. That's the bottom line. We don't really know. It's odorless, it colourless, it moves fast. What are we going to do? The only thing we can say is the cracks are very rapid growing and they're not connected with corrosion. So something else is happening. Okay. So that's all I was going to say about types of localized corrosion with stress. So we've now covered the types of corrosion in terms of mechanism. When we started off, we talked about electrode potentials and thermodynamics. The next thing to talk about really is some of the kinetics of the corrosion rate in terms of polarization curves. So that's what we're going to talk about next. See what it says there. That's all right. Okay. So the overpotential quite often is given this Greek symbol, a sort of curly N, which is eta, and that value for this first stage of polarization relates to the activation energy for the electron transfer. So you've got an electrode surface, you've got some, you're either generating, well, okay, we're making iron 2 plus 2 electrons from iron. So we've got to then take those electrons and whiz them round to the cathode, and the if you like, the transfer of the electrons away off into the circuit. The electron transfer here is a very fast process. Electrons are like hydrogen; they move very fast. They're even smaller than hydrogen, move even faster. So it's not that the reaction is being slowed down. It's not that it's being limited in that sense. But there is an energy required to do the transfer from iron to iron 2 plus and those 2 electrons. So there is an activation energy to be exceeded. And what that means, if you look at potential against current, is when you've got no current, you've got an equilibrium potential value somewhere. But if you start current flow, if you actually start this reaction going, there has to be a potential change, and usually a little potential drop, and then it'll steady out. Okay, so that initial little drop is your eta value related to the activation energy, the amount of overvoltage you need to apply to get the electron transfer to occur. So it's a thermodynamic value. The result is on an Evans diagram, which is what a potential current plot is, you get a linear response after you've got over that initial energy kickstart to the process. If I just show you one of these. Actually, I've got one on the handout. It's not as good as this one. Okay, this is a sketch just illustrating what happens if you've got activation polarization, potential against not current, and you get a linear response once you've got over the initial potential change required to activate the process. And what we've got is 2 processes here, one which is a cathodic process and one which is an anodic process. And the slope of the line that you get for E against I after you've got over the initial kick start is characteristic of the reaction that's occurring in the cell. So the slope of the line for, say, iron 3 plus 3 electrons will be different from the gradient of the line for iron 2 plus. And they're called Tafel slopes, after a guy who identified this as a way of looking at trying to identify mechanisms in corrosion cells. That's our free corrosion or equilibrium potential before we start to move away from equilibrium. And maybe the way to think about it is that this is all about Ohm's law. So I equals V over R. Current equals the voltage over the resistance. In our cells, we tend to call V E. It's just a convention. But in in electronics or physics, use V. And you could see that you'll get a linear response, which is what we're getting in our plot. And they're called Evans plots, so they show the behavior of the material when there isn't any other forms of polarization going. So, activation polarization, electron transfer speed, which is very fast, and it's just exceeding the activation energy to get that transfer to start going. And that gives you a linear response on the Evans diagram, the E against I plot. The other two types of polarization relate to changes in the cell. You get concentration polarization, and then you start getting a nonlinear current potential response, and you also get resistance polarization. Excuse me. So initially, when you start your process, the concentration of the electrolyte is uniform, and you begin to slowly react species at the anode and cathode, and then you end up with a concentration gradient between the bulk solution, which is still or more or less under equilibrium conditions, and the solution near the electrodes, which has now changed because reactants have been used up to produce corrosion products, and you've got oxygen reduction or hydrogen reduction at the cathode. So you've then got a concentration gradient, and we've got a situation now where you can't just carry on increasing the current. So if you're plotting potential against current, initially, as you move from your equilibrium position, you'll get a linear response. I'll draw it the other way, actually. Choose the other way. Get a linear response of You change the potential, you increase the current. That's fine. But eventually you get to a point where the current can't increase any further, even if you do increase the potential further. And that's because you've reached a diffusion limit. The ions can't migrate any faster through the solution. So this is concentration polarization because there's a physical limit on the maximum current you can get because of the diffusion of the ions in the electrolyte. If you were dealing with an electronic circuit or just had activation polarization, you carry on going linear. But that's not the real world. So in an Evans diagram, you get the straight line plots. In a real polarization curve, which we're going to talk about in a minute, you'll actually see curved plots. And then the resistance polarization, well, if you're using Ohm's law, I equals V over R, clearly if R changes, then the IV response is not going to be linear. And the R will change because corrosion products will build up on the surface of the electrode. So you might get filming, you might get passivation, perhaps, depending on the system. Anything could happen on the surface of the electrodes, and the solution conductivity will change because you are consuming reactants and generating products and dumping them into the solution. So you've got R film plus R solution. And they're two variables that affect the current voltage response. Okay, that's a reasonable place to stop. I'll see you next week, unless you've got any questions. Oh, that's a good time. I think that's a fire alarm by the look of it. I think we need to orderly leave the building. Okay. Okay, it doesn't sound like a drill. I think we'll have to go.